Okay. Now, I have a whopping 4 pages of notes to cover. So let's see if I can get through them all. At some point, I want to talk more about how to get things done in MATLAB. But I don't know if I'll be able to do that today. But today is actually the only ever day that I'm covering finite difference stuff. Next week I get into special methods. But so at least by the end of today's material, you'll see no material for homework 1 in its entirety. Okay, so focus on how you solve this. What I said last time was how to come up with finite difference rules for various derivatives. Also forward, backward difference, center difference for the first and second derivative. Now we're going to focus on the specific PDE, Poisson's equation. And I'll show you how you can solve it numerically using finite differences. All right, so the problem we're going to solve is minus uxx is equal to f on a domain x going from 0 to 1. And I'm going to impose different types of boundary conditions. So on the left boundary, I'm going to use a Dirichlet boundary condition by specifying that the value of a solution at x equals 0 is equal to this given value a. Then on the right boundary, I'm going to impose a Neumann boundary condition specifying that partial due respect to x at x equals 1 is equal to this given value c. All right. Okay. Now, when you're going to solve, you're going to take a PDE or already discretize it and go with a system of algebraic equations to solve. Very first thing you need to do is specify how exactly are you discretizing the problem. So what we do here is define a grid. So my x values will consist of grid points 0, h, 2h, and so on, all the way up to n times h and then 1, where the spacing h is equal to 1 over n plus 1. Okay, so this is the kind of spacing you want to use when your grid is to include n interior points. And then we also have 2 boundary points, x equals 0, x equals 1. Now, what grid you use depends on the boundary conditions. For instance, so like if you have Dirichlet boundary conditions at both ends, you want to, your grid consists of interior points. You might use boundary points to help set up the equations, but you're solving for u at the interior points because at the boundary points it's already known. Here we have a Neumann boundary condition. So we are going to solve for a value of a solution at x equals 1, not at x equals 0 because we already know that it's equal to a here. So we're going to solve for u at n plus 1 points, the n interior points and this right boundary point here. If you have periodic boundary conditions, you would include all the interior points and 1 boundary point, but not the other, because you have wraparound, like the value at the right endpoint is a value at the left endpoint, so you only need 1 of them. So the point is, the boundary conditions influence what you choose for your grid. All right, so each grid point is given by I, xi is I times h. I going from 0, 1, up to n plus 1, for the n plus 2 points in total that we have in our grid. When you have a Neumann boundary condition, you're specifying the value of a derivative at a boundary point. So what you might need to use, and what we will use, are occasionally points that are outside the domain. Those are called ghost points. So we will use a ghost point, and that'll be xn plus 2, which is equal to 1 plus h. So same spacing, we just go one step further outside of the domain. Now, we're not going to solve for u at that point. We can't, because it's not in our domain. But it will help us set up the equations we need to solve for u where we do want it. All right. And I then define u sub I to be our approximation of the exact solution u evaluated at xi. So the ui's are unknowns, or to be more clear, values we'll be solving for are u1, u2, up to un plus 1. So value of u of x at all the interior points and the right boundary point. What is known right now is u0 is equal to a because of a left boundary condition. U of 0 is equal to a. Questions about the notation up to this point? So we're going to replace the PDE by an equation that approximates uxx using finite differences. So we discretize PDE. Here's what we get. So we have minus, and then the uxx is replaced by a center difference formula. Ui minus 1 minus 2 ui plus ui plus 1 all over h squared. Plus the error. So that all this right here is exactly equal to minus uxx. And that is equal to the right-hand side, where we're just going to evaluate the function f at, well, okay, let's call it f of xi, but it's common to abbreviate this as f sub I. So you can think of defining the vector of f values. Fi is f of xi. Just as ui is u of xi. And we're going to use these equations for every point at which we want to obtain the solution. So this holds for I equal to 1, 2, up to n plus 1. So in other words, all the interior points and the right boundary point, because those are the points at which we don't know what u is. Now, setting up our equations to solve, this we're going to neglect because for h small, the error is over h squared, which is particularly small. And we don't have a handle on what this is anyway. So, so really we're going to solve a system of equations that features this center difference and this right-hand side. And that will give us our approximation of u of x. Questions at this point? Now, so what we have here is a system of n+1 linear equations in the n+1 unknowns that we have here. So that can be described in matrix vector form. The problem is we have yet to take boundary conditions into account. And when we're dealing with points that are near the left or right boundary, those boundary conditions are going to have an influence on the equations. So before we can actually write down the system we're going to solve in matrix vector form, we need to account for those boundary conditions. So, what are the n+1 equations that we have? So I just work from left to right. I wrote down an equation for I equals 1, 2 up to n+1. So I'm going to focus on the case of I equals 1. So from the leftmost point. So we're going to have minus, and then I have u0 minus 2u1 plus u2 over h squared is equal to f1. So I'm just reproducing the equation I had written earlier, just filling in I equals 1. Now, since we're going to have a matrix vector product, what is the vector? So our goal is a system of linear equations, A, U is equal to F. And as of right now, the only thing that is completely known is what U is, or at least the form of it. It's still our unknowns. That's annoying. Okay. So U consists of U1, U2, up to UN plus 1. So any terms that we see in this equation involving U1 up to UN plus 1, that deals with the matrix vector product, A times U. Any other terms will go on the right-hand side, because those don't correspond to our unknowns. So that includes F itself and any boundary terms that we might get. So, anyone tell me how the boundary conditions come into play for this equation?
C.
Yes, U0 is equal to A. So this is how we take a Dirichlet boundary condition into account. This term has to go to the other side. So now I'm going to have 2u1 minus u2 over h squared is equal to f1 plus a over h squared. So this is what happens in equations corresponding to points near boundaries that we tend to get boundary terms. When it's a Dirichlet boundary condition, you're just substituting in the known value at the boundary. Like you substitute over here, move a term over to the other side. So the left boundary condition is handled. Questions about that? Now let's look at I equals 2. The minus of nu1 times 2u2 plus u3 all over h squared equal to f2. Now, are boundary conditions going to have any impact on this equation? No, we're not, because these are all values at which we're interior over right boundary, points at which we're actually computing u. There are no bound, like if u0 or un plus 2 appears, sorry, un plus 1 appears, that's where we have to worry about boundary conditions. We have neither of those in this case. So in fact, I can do this for I equals 2 up to n minus 1. We'll have these equations. That is actually exactly what I've written down earlier. So for all of these values, we can leave it as is. So nothing interesting there. And for the last equation, actually this is true for I equals 2 up to, well, yeah, up to n, this works. Okay. I is equal to n plus 1. We have
the n plus 1.
So we have ui n minus 2u n plus 1 plus u n plus 2 over h squared equal to f n plus 1. Okay, so what's the problem here?
2 is belong to the zero.
Yeah, it's not one of our unknowns. And unfortunately, it's not like the Dirichlet boundary condition. Here we had u0 that was not one of our unknowns, but we knew its value, so we just put it in. Can't do that here. So knowing boundary condition is a little more difficult to handle. So how do we handle it? We discretize the boundary condition. All right, so we have our right boundary condition is ux at 1 is equal to c. So we can discretize this by a finite difference. We use a center difference. un plus 2 minus un over 2h is equal to c. And this is an approximation of du dx point n plus 1, which is at x equal 1. In fact, we say this is equal to du dx at this point plus an error that is order h squared. So this entire fraction is equal to this. Now, I actually have some choice here. I could have used, for instance, a forward difference. UN plus 2 minus UN plus 1 over H is equal to C. That would have been fine too, except for one thing. A forward difference, what is its accuracy? Like the center difference is order H squared. If I use a forward difference, what would I have? Order H is first order accurate. The center difference I use for my PDE, that's second order accurate. You need to make sure that you're using, you keep your order of accuracy consistent across whatever derivatives you're approximating, whether they come from a PDE or the boundary conditions. Because even if I use this second order center difference from a PDE at all of my points, and if I use a first order accurate approximation of du dx at this one boundary point, that would have tainted the whole solution, made it the whole solution only first order accurate. But by using a center difference, I have second order accuracy everywhere. Now, they would tell me how I can use this equation to help me with this one. Because I don't want UN plus 2 in there. Yeah. I can use this to solve for UN plus 2. So UN plus 2 is equal to UN plus 2HC. And then I can substitute that into that equation over there to eliminate that ghost point. So what will that give me? I'll have minus out front, and I have 2UN, because UN plus 2 has a UN in it, which adds to the other UN, giving 2UN minus 2UN plus 1, all over H squared. And then I'm going to have this other term. So I'm going to have, so equals Fn plus 1 plus 2C over 8. So I have 2CH from there, included in here, divided by H squared. So I get 2C over H. I actually need to check. Yeah. Oh, there's a question there.
No, not yet. I'm trying to solve it.
Okay.
I don't know why, but my units got canceled. I think I made a mistake with this.
Oh, yeah, because this minus is sitting on the outside.
Yeah,
These terms have the same sign.
that's what I.
Okay, so I'll put them. Yeah, the minus up front is because there's a minus in front of UXX. All right. Well, now I have all my equations and both boundary conditions accounted for. So now I can write down my system in AU equals F form. So the elements of F, most are just equal to Fi. But the first element is F1 plus A over H squared for the left boundary condition. The last element of the vector F has last element of Fn plus 1, and we add on this 2C over H. Now, for the matrix, we need to look at the coefficients of the U values throughout these equations, and those are our matrix entries. And for each one of these equations, I going from 1 up to n plus 1, if we look at the coefficient of ui, that goes on the main diagonal. The coefficient of ui minus 1 goes on the subdiagonal. That's right below the main diagonal. And then the coefficient of ui plus 1 goes on the first super diagonal that's right above the main diagonal. So I can write down what A is. Notice we have a denominator of h squared throughout. So I'm going to, and we have minuses all over the place. So I'm going to put a factor of minus 1 over h squared out front. Okay. So with a minus already sitting out there, I can focus on what's multiplying the u values inside these fractions. So on the main diagonal, I'm going to have minus 2 all the way down. On the subdiagonal, I'm going to have plus 1. Except for the last row, where it'll be a 2. So all 1s and then a 2 in the last row. And then the super diagonal, we're going to look at the coefficient of ui plus 1. We're going to have, okay. Actually, I'm going to write it this way. Minus, yeah, okay, just for consistency with the other equations. So I'm going to have plus 1. Okay, and all the way down to the second to last row, yeah, it'll be all ones. Yeah, I can fill in more of these entries toward the end, just for clarity. So we have 1, minus 2, 1. Okay. Okay, so that is your matrix. And the vector f, just to summarize. So we have f1 plus a over h squared, first element, then f2, and so on down to fn. Then I have fn plus 1 plus 2c over h. Okay. The question's about where the matrix came from. Okay. Now, so I could just go ahead and solve the system of equations. The matrix is tridiagonal. So if you use, for instance, Gauss elimination, it would be quite efficient. So for a matrix of n plus 1 by n plus 1, the system can be solved in order n floating point operations. So that's quite nice. But now, there is one change that's a good idea to make to this matrix, though. And it's not absolutely essential, but for a person's numerical solution, it's advisable. And that is, if I were to take the last row and scale it by a factor of 1/2, then I'd have 1 and minus 1 here. And then I'd have to scale the right-hand side by the last element by 1/2 also. Can anyone tell me what nice property the matrix now has because I scaled that last row? Well, it's banded anyway. But there's something else that happened to the matrix. It's a property that it now has and didn't have a second ago. It was vertical anyway.
The subdiagonal and superdiagonal are identical.
Yes. In other words, the matrix is now symmetric. So that's what I was doing. So scale the last row for symmetry. And the reason why that's a good idea is methods for solving symmetric systems of equations require half as many floating point operations as unsymmetric. For example, a Gaussian elimination for a general matrix, it takes 2/3 n cubed operations, whereas Cholesky factorization for a symmetric positive definite matrix takes 1/3 n cubed. So in general, having symmetry cuts the number of operations in half. So yeah, not essential, but if you make things twice as fast, why not? Okay. So these kind of banded systems are what we often get from if you're solving a one-dimensional PDE using finite differences. Those are kind of matrices you get. Any questions about what happened here? Now, okay, now what we do is spend the rest of the time talking about convergence analysis. Like, because what we want to do is when we use methods like this, presumably the errors order h squared, but we want to confirm that. I would like to know that as the grid spacing h goes to 0, that the computer solution we're getting is actually converging to the exact solution. Okay. All right. Yeah, for some reason I have it in the notes solving a PDE. U double prime is equal to F rather than minus U double prime is equal to F, but so I'm gonna think of that because it's deep notes. But still Poisson, so minus F into that. Okay. Now, I'm going to let U hats consist of values of the exact solution at my grid points. Okay, all right. And I'm going to assume Dirichlet boundary conditions on both ends. So this is not a problem that I was just discussing, but it's just a related problem. So that means the grid points that you use are only the interior points. All right. And U of xi refers to the exact solution. Which to us, of course, is unknown, but we're just using it for convergence analysis. Okay. And we're going to assume that we have a finite difference discretization, like before, that leads to a system AU is equal to F. Okay. So in this case, our matrix A is 1 over H squared out front, and we have -2 to the diagonal, 1's above, 1's below, because of its Dirichlet boundary conditions on both sides. The vector F consists of f of x1 down to f of xn. Okay. So in this case, the discretization is more straightforward because we only have Dirichlet boundary conditions that are easy to handle. Actually, I'll check my. Okay. Okay, I'm going to assume also that the boundary conditions are homogeneous. That U is equal to 0 on the boundaries.
Yeah. What about E squared? Is it negative?
No, because it's just U double prime, not minus U. Yeah. Reason why I'm assuming homogeneous boundary conditions is so I don't have to have any boundary terms in here. For making things as simple as possible. Actually, have to make a note of that. Here are the notes. Okay. So with this in mind, I need to find two kinds of error that will help us in our analysis. Local truncation error. Abbreviated as LTE, is defined to be tau equal to A times U hat minus F. Tau is a vector. Okay. Now, different problems have different notions of local truncation error specific to that problem. But there's one thing about local truncation error that's the same no matter what problem you're solving for. The way you get it is you substitute the exact solution. What?
When we did it, for approximate solution of the problem is exact solution of the nearby problem.
That's related, but not really what we're doing here. Yes. Okay. Into numerical scheme. Because if you think in terms of all the possibilities, substituting the exact or computed solution into the PDE or numerical method. Well, it doesn't make sense to substitute the numerical solution into the original PDE because the numerical solution is only defined on a grid, whereas the PDE deals with a continuous function, so forget about that. The exact solution, of course, satisfies the PDE exactly. The numerical solution satisfies the numerical method exactly. The only combination left is exact solution substituted into numerical method, which it is possible to do because even though the exact solution is a function of x, you can evaluate it on the grid and take those grid values and substitute into this equation. And because the computed solution is only an approximation of the exact solution will not satisfy the numerical scheme exactly. There's going to be something left over. And if I plugged in the numerical solution here, this would be 0. But by plugging in the exact solution, I'll have something, and that's my local truncation error. Okay. Another way to think of it, because we're dealing with a system of linear equations here, it's the residual. Actually, it's minus the residual of this linear system. Okay. Okay. So actually, taking the flip side of what you were bringing up, let's say that the exact solution solves the nearby problem. Nearby. AU hash is equal to F plus tau. And normally that's meant to used to talk about the computed solution as the exact solution nearby problem, but now we're looking at the other side of that. Okay. Now, one of the nice things about working with the exact solution is we can get an expression, a useful expression for the local truncation error using techniques such as Taylor expansion. So that's what I'll do here. Since I have my matrix right there, right, so tau I, so I'll show you each element of the vector tau. So AU minus F. So if I carry out the matrix vector multiplication, A times U hat, what I would get is 1 over H squared, and I'll have U of X I minus 1 minus 2 U of X I plus U X I plus 1 minus F of Xi. But this is the center difference approximation of a second derivative, and I wrote down the error formula for that last time. So this is equal to U double prime at xi plus an error term, which is plus 1/12 fourth derivative of U at xi plus times H squared. And then there'll be additional terms that are to continue Taylor expansion that are order H to the 4th minus F of xi. But here's where we use the fact that U is the exact solution. U double prime is equal to F. So these terms cancel. So a local truncation error is h squared over 12, fourth derivative at u, plus lower order terms that are ordered h to the fourth. So the local truncation error is order h squared, which is what we'd expect because that's what we get from the center difference. Any questions about that? Now, while this will be useful to us, this is not the kind of error that we're actually looking for. That's where I need to introduce the other concept, the other notion of error. All right. That is global truncation error. GTE. And that is defined to be a vector E equals U minus U hat. So straightforward idea of error, computed solution minus exact solution. So really we want to make sure that that goes to 0 as H goes to 0. So now I'm going to multiply both sides of this defining equation for a global truncation error by A. So it's AE is equal to AU minus AU hat. But AU is equal to F. Well, what's F minus AU hat? Or minus tau, yeah. So minus the local truncation error. So the global and local truncation error are related by A. Okay. The way to look at it is the error, the global error, satisfies the same PDE as the original, except that the right-hand side is different. Instead of it being F, it's equal to minus the local truncation error. And okay. So I'm going to use this relationship to try to get a handle on can we prove that the global truncation error goes to 0 as h goes to 0? And if it does, at what rate does it go to 0? Because we know that the local truncation error goes to 0 as h goes to 0 at the rate of order h squared. Is the same true of the global error? What we can do is use this equation. So A E is equal to minus tau, and take the norm. Oh, actually, no, that's right. I'll solve for E. E is equal to minus A inverse tau. Then I take the norm of both sides. So the norm of E. Actually, what I'm going to do here is I'm going to include superscripts of H to make clear that everything we see here depends on H. So if we're given spacing H, the global error is less than or equal to the norm of H inverse times the norm of local truncation error. That's just a property of matrix norms that we have back. Okay. So what happens to this as H goes to 0? This part goes to 0 as H goes to 0, so that's fine. We want this to go to 0 as H goes to 0. But what about this? We don't know. How do we know that the norm of the inverse is not going to infinity?
Because of the 1/8 squared.
Well, that could be a problem. We need to be sure about that. Okay. All right. So now I'm going to give some definitions of the three essential concepts of convergence analysis for this problem. Okay. All right. So we say that numerical scheme AH UH equals FH is first consistent if the limit is H goes to 0 of tau H is 0. So in other words, the local truncation error goes to 0 as H goes to 0. We say that it's consistent in that case. We say it is convergent if the global truncation error goes to 0 as H goes to 0, where EH is UH minus U hat H. Okay. Just the way the definition I given before. That's what we really want, is convergence. Consistency is relatively easy to determine because we can use Taylor expansion. So how do we know if consistency implies convergence? Well, it doesn't necessarily. We need one more thing. The scheme is stable if there exists some spacing, which I'll call H naught, such that for H less than H naught, the norm of the inverse is bounded by some constant C. For some C that has to be independent of H. Another way of putting it is this norm must be uniformly bounded. So right now we have this. So if it is stable, then we have that the norm of the global error is less than or equal to the constant C times local truncation error. And because we already know that this method is consistent, this would imply that it is convergence. And the global error is order A squared. Now, for stable schemes, generally, the global error will have the same order as the local error. But, so the idea is you figure out what the local truncation error is. You prove that your scheme is stable. And then you can conclude convergence. Question about this?
So does convergence implies the other two?
Well, that's what we need to talk about now. So what I've actually just stated, that a scheme is consistent and stable as convergent, that's one half of an important theorem. That is the Lax equivalence theorem. The Lax equivalence theorem states that you have your scheme is convergent if and only if it is consistent and stable. So yes, we do have that implication. Furthermore, if a local truncation error is order h to the p for some p, then the global truncation error is also order h to the p. And what I've shown you involving these norms shows why that is true. So I've proven one half of it. And if you have consistency and stability, you have convergence, and you have this order of accuracy. I've not shown, and I will not, that if it's convergent, it's also consistent and stable. No time for that. But I'm not going to make you do it either. All right. So any questions about that? The Lax here is Peter Lax, who was a professor at NYU. I believe he's still alive. I imagine he must be retired by now, but well, let's find out. Yes, he's 96 years old. So, but he would visit Stanford now and then, so I would see him there. He probably, I don't know if I ever actually like met him. I know I didn't give a talk in front of him, I wouldn't have been nerve-wracking. And okay. Oh, wow. On his Wikipedia page, there's a discussion of an incident in 1970, part of an anti-Vietnam War protest. A group of students, called the Transcendental Students, took a supercomputer at NYU hostage. And Lax itself had been instrumental in acquiring that computer. They demanded $100,000 ransom to provide bail for a member of the Black Panthers. And the students tried to destroy the computer with explosives. But Lax and his colleagues managed to disable the devices and save the computer. Yeah. Wow. Odd things I remember about him is when I would see him like at seminars, and he would sit there in front, and as the speaker was doing their thing, he would soon fall asleep. And when he really felt like his head would be tilted back. Yeah. And then the other weird thing is that when he was the speaker, but back then, a lot of people like including himself would use a overhead projector with transparencies, very low tech. And you would think that most people, when they're using transparencies, they would either use a pointer, a stick, and point on the screen, or they might point their finger on a transparency, see what they're pointing at, but not him. he would put his finger out in the air and to put it what he wanted to. It seems so odd, like doing it the hard way, but okay. Yeah, so.
How old is he?
He's 96 years old.
Oh, okay.
Yeah, so. There's a lot of American weapons named after him, like the Lax Friedrich scheme, the Lax Wendroff scheme, and we'll see some of those toward the end of the semester for time-dependent problems. Okay, now, dang, music on time. All right, now, the only thing that I haven't done here is I have not shown you that this method is stable. We need to actually establish that for this particular method for Poisson's equation. So now I'm going to do that. So that'll be the last piece of the puzzle that will establish stability from which we can conclude convergence. All right. So is it stable? So for that, we need to look at, and I've not specified a norm to use, but we can just choose a norm because norms are generally equivalent. Okay, so I'll use a 2 norm. So the matrix in this case is symmetric. That's important because then we can say that the 2 norm of A inverse is the spectral radius of A inverse. That's only true when it's symmetric. Now that is defined to be the maximum of the reciprocal of all the eigenvalues of A. And all the eigenvalues of A are non-zero because it's invertible. So the largest reciprocal, so that's going to be, if we take the smallest eigenvalue in absolute value and take reciprocal of that, that'll be the norm. So what we need to do is we need to get a handle on what is the smallest eigenvalue of our matrix A, or AH, and make sure that it's at least bounded below independently of H, so that its reciprocal will be bounded above independent of H. Okay, now what helps us in this case is we actually have a formula for the eigenvalues of A. So lambda I is equal to 2 over H squared cosine of IIH minus 1. Okay. Now that formula itself doesn't help us, but what we could do is carry out Taylor expansion. On the cosine, so that would be 1 minus 1/2 I pi h squared plus 1/4 cosine at some unknown point, twiddly, of I pi h to the 4th. Okay, so by using a Taylor remainder, I can terminate the Taylor expansion. Oh wait, the 4th derivative of cosine is cosine, so yeah. And then I have a minus 1. So the ones cancel. And then we have a cancellation of h squared. So we have So we have minus I pi squared as the leading term. Okay, hold on. Okay.
It's the index and not I.
Yeah, it's not the imaginary infinite. I have P in the notes, but I also am using the Greek letter rho. I didn't want to cause confusion, so yeah. All right. Okay. Now, if we look at the take the absolute value, the smallest eigenvalue. So the smallest eigenvalue is going to be minus pi squared plus something that is going to 0 as h goes to 0. So that tells us that the norm of AH inverse, we'll be taking 1 over this, is approximately 1 over pi squared. So yeah, we can say that as h goes to 0, that the norm of A inverse is uniformly bounded. This is not totally rigorous here. But the idea is, what's important is that as h goes to 0, the smallest eigenvalue is not going to 0. So that way we can be sure that 1 over that is not going to infinity. And that's how, so because of this term right here, that is what saves us, gives us stability. What's so nice about a PDE like this, the Poisson equation, there's only constant coefficients. The convergence analysis is relatively easy because we happen to have this nice formula for the eigenvalues, which you're not going to have for PDEs in general. So I feel really bad for one of your fellow graduate students, Kelly Ruster, who's doing convergence analysis about variable coefficient PDEs, and the proof's getting way out of hand just because it doesn't have any of the simplicity of this problem. But hey, it's getting done. Okay, so all right, there's only a few minutes left. That's the end of the notes, but our homework questions. Okay, all right. Yeah, I'll see if I can make sure that there's some time in like next week's classes. Okay. Till next week.